Hi everyone, today we're going to be talking about topic 8.10, buffer capacity. So buffer capacity in simplest words is basically the amount of acid or base a buffer can neutralize before the pH begins to change. And if I increase the concentration of both HA and A minus, my buffer capacity also increases. In other words, if I increase both the acid and conjugate base, I can add more acid or base to it, and it will resist the change in that pH. And so the more amount of HA and A minus that are in there, the more that my buffer can actually resist pH change, as long as I increase both of them together. Now, the pH range is the range of pH values where a buffer system actually works effectively. Now, buffers are most optimal when pH equals pKa. Now, if you remember, this is about halfway to the equivalence point in a titration. So around that point is when our buffer works the best. Another way to say this is when the concentration of HA is equal to the concentration of A minus. If you plug in the same concentration into the Henderson-Hasselbalch equation, you'll find that pH equals pKa. That's why that trick actually works. And if the concentration is more than 10 times the other, let me rewrite this, but if the concentration of one species is more than 10 times of the other, the buffer is poor. And what this basically means is the pH range of the buffer is plus or minus 1 pH unit from the pKa. And so as you get to about 10 times more the concentration, right, your buffer isn't working as well anymore. And now your pH is about plus or minus 1 from what the pKa actually is. And so let's say we get a problem where we're interested in finding the pH of a buffer when strong acid or strong base is added to the system. How do we do that? Because that's a question that we're going to be asked on our quizzes and exams. So if you add a strong acid or strong base, it's of course a neutralization reaction. Neutralization meaning the H plus from the conjugate acid that's in there is going to react with the OH minus, and it's going to form water. Now, depending on whether or not you add acid or base, if you're adding acid, right, you're giving it H plus. If you're adding base, you're giving OH minus. So you're going to calculate it just like a stoichiometry problem to find the concentration of HA and H minus, then use the Henderson-Hasselbalch equation. So first, stoichiometry. Second, Henderson-Hasselbalch equation. That's essentially the workflow we're going to do for this. This is just looking at it in more of a picture format. And so let's say I have a buffer. It's got HA and it's got H minus. If I add strong acid, I go by this top pathway where I'll have A minus, which is the conjugate base that's in my buffer. I'm adding H plus, which is my strong acid, and I'm going to make more of the weak acid. I calculate the new values of HA and H minus as using this equation up here, and again, just doing a stoichiometry calculation. Then I use the Henderson-Hasselbalch equation to find pH. For a strong base, it's the exact opposite. And so the equation here is the weak acid that's in my buffer reacts with the strong base to form a conjugate base, and of course, we get water at the end. So after you calculate the new values of HA and H minus, you then again use Henderson-Hasselbalch. And so this workflow works for any of these buffer problems. Okay, so here's an example of how you can actually do one of these problems. It says we have a buffer is made by adding 0.300 moles of acetic acid and 0.3 moles of sodium acetate to enough water to make 1 liter of solution. And so you can see here we're this entire thing is at 1 liter, and so in this case, we don't really worry about volume. We can do everything in moles. So do math in moles, because the volume for the solution is entirely the same. We already know the max volume is 1 liter, so we can just do everything in moles. So calculate the pH, essentially what we're being asked is calculate the pH after 0.02 moles of NaOH is added. And so we know OH minus is going to react with acetic acid because, right, the base reacts with the acid. And so what we can do is we can write out an ice table to see what actually happens stoichiometrically. And so this is essentially step 1 of this process. So I said on the last slide that we can use a Rice table. Let's first write out our equation. We're adding NaOH, which is the same thing as just adding OH minus ions to the solution. And so we have our HC2H3O2. That's our weak acid. It reacts with OH minus, and it just is an acid-base reaction. We get C2H3O2 minus plus H2O. That's our reaction initially. If we go back to the last slide, we're told that we added 0.300 moles of this. We're also told that we add 0.02 moles of OH minus. Initially, we have the same amount of acetate, 0.300 moles, and of course we always ignore the water in the reaction. Now let's look at our change. Of course, all we're doing here is a stoichiometry problem, and so we just need to look at which one's the limiting reagent. In this case, our base is limiting, and so we use all of our base. So the change is just the amount of moles of base I put in. In the reactants, it'll be minus the same thing, and in the products, I essentially add 0.02 moles because I'm adding, base to it, and so I should make more conjugate base. And then for equilibrium, all we do is just add these together. 0.3 minus 0.02 is 0.280 moles. 0.02 minus 0.02 is just 0. And then 0.3 plus 0.02 is 0.320 moles. And so now these are the concentration of HA and the concentration of A minus. And so what I've done is step 1 is completed. Now the workflow for this is I said that step number 2 is to use the Henderson-Hasselbalch equation, which, as a reminder, pH equals pKa plus log concentration of A minus over concentration of HA. Now, in a problem like this, obviously you're going to typically be given the pKa. In this case, the example didn't write it out, but pH, the pKa of acetic acid is 4.74. You will always be given that unless you're trying to find the pKa, in which case you should normally be given the pH, plus log, and then we just use the values that we calculated on the last slide. We made more A minus, so we have 0.320 moles of A minus, and we reacted some of our HA. We were left with 0.280 moles of HA. In this case, because the volume is the same, we don't have to convert to concentration. We can just directly use the number of moles. And if we do this calculation, we get 4.80. And so we can see the pH is still pretty close to the pKa of our acid. So let's look at this next example here. This is the case of where we add acid, and there's also another change here. We can see here where the concentration of A minus is 10 times the concentration of HA, and so we should have a pretty bad buffering capacity here. And you can see that's true. If we calculate the pH of this buffer here, you see 4.76, which is the pKa we're given, plus log of 1 over 0.1, we get 5.76. And so the pH is really different from the pKa. And so we're told if 0.05 moles of HCl is added to the buffer system, we're going to assume no change in volume. It will react with the acetate ion, and the amount of acetate of acetic acid will increase. And so we can actually show that and also calculate what this new pH should be. So we use a Rice table, as always for these problems. Our reaction here is because we're adding acid to it, it reacts with the conjugate base. And so C2H3O2 minus plus H plus reacts to form HC2H3O2, right? And I can do this with H3O plus and water, but for the sake of simplicity, I won't do that. We know how much acetate we start off with. We start off with 1 molar. We're assuming no volume change, and so we don't necessarily need to worry about converting to moles and then reconverting into volume. We add 0.05 moles of HCl. And we know that we start with 0.1 molar acetic acid. So we can add that right here. Change, of course, our H plus is our limiting reagent here, and so that is what determines how much change we have. We have minus 0.05 here, minus 0.05 here, and plus 0.05 here, and then we just add things together for the change. We get 0.95, we get 0, because that cancels out, and we get 0.150 molar. And so that was step 1. Step 2 is to just use the Henderson-Hasselbalch equation. So our new pH, pK stays the same because that's just determined by the kind of acid we have. Plug everything in. 0.950 divided by 0.150. When we do that math, we get the new pH is 5.56. And so the change in pH here is actually 0.20, which is quite a lot. And that's exactly the point I'm trying to show here. If you have more than 10 times the amount of A minus or HA, you're going to have a more drastic change in your pH. We'll do some more practice with this in class, but for now, that's all. Thanks, guys.